Concept of stability. The concept of stability is very important in analysis and design of control systems. So now let us look at what are the definitions of stability. So a LTA system is said to be stable if the system is excited with a bounded input, if the output is also bounded. Usually it is called BIBO stability, bounded input, bounded output stability. And in the absence of input, if the output tends towards zero or any equilibrium state. So this kind of stability is usually called asymptotic stability. So generally we use bounded input, bounded output stability to find the stability of the given system. Let us look at the transfer function in the polynomial form. C of s by r of s is equal to so b naught into s power m minus 1 and plus we know this polynomial form divided by a n into s power n plus and so on. So for this particular polynomial transfer function, and I can write c of s by r of s as g of s. Now what is c of s? Your c of s is nothing but I have g of s into r of s. When you apply the convolution to this, then you will get a c of t as integral 0 to infinity. It is a convolution integral. We will get g of tau r of t minus tau d tau. So this is the convolution. Now what is g of tau? Which is nothing but the impulse response of the system. What I can say now, a system is said to be stable if the impulse response approaches to zero for large amount of time, that the sufficiently large time, if a g of this tau is going to be zero, means the impulse response is reaching to zero, then we say system is stable. A system is said to be unstable if the impulse response approaches to infinity for sufficiently large time. So we need to wait till it goes to infinity, or if it is continuously increasing also we can say system is unstable. If the impulse response approaches to a constant value for sufficiently large time, then the system is said to be marginally stable or critically stable, or we can say sometimes a verge of instability. Our system response is oscillatory response. Our system is said to be oscillatory system. That means by looking at the impulse response, then you can find out what is the stability nature of the system. It can be stable, unstable, marginally stable. We have basically three conditions of stability. Let us look at the relation between the location of poles and its impulse response. Right, the first case I am taking g of s as 1 by s plus a. When you locate the pole on s plane, it is located s is equal to minus a. What is impulse response? E power minus at. When you look at the impulse response, when you plot here, so it is decreasing, exponentially decreasing, means your impulse response is going to zero for sufficiently large amount of time, then we say system is stable. So e power minus 8 term always gives the stable response of the system. Therefore whenever a pole lying in left of the s plane, my closed loop system is stable. Second case, let us take the transfer function 1 by s minus a, means I have s is equal to plus a. There is a pole in right half of the s plane. Then what is g of t? Then e power at, exponentially increasing term. So it is exponentially increasing like this. So when you look at for large sufficient time, then it is keep on increasing. At t is infinity, the value is also infinity, which is unbounded. So we say system is unstable system. So whenever a pole exists in the right of the s plane, we say system is unstable. Similarly, when you look at the condition like this, I have one pole in the right of the s plane, two poles in the left of the s plane. So when you write a g of t, then the first one term it is e power minus at, and another term is also e power minus at, other term is e power plus at. Means the first term is going to 0, the second term is also going to 0, the third term is continuously increasing. For large amount of time, let us say time here, the value, these two are 0, but this value still exists. Means, so the final response, because it is a linear system, so I can add all the responses, the final response is to keep on increasing only. So even if you have one pole lies in the right of the s plane, even the remaining poles in the left of the, any number of poles in the left of the s plane, the impulse response of all the poles in left of the S-plane going to 0, but the pole which is there in the right of the S-plane is continuously increasing, results the whole response is also continuously increasing. So we say system is unstable. So why we always look at the pole locations, why can't zeros? But when you take any zero, let us say I have some, let us say s plus 2 by the denominator s plus 1 into s plus 4 into s plus 5. So when you are trying to find the inverse Laplace transform of it, that means impulse response of it, your numerator term is going to be a coefficient of your e power terms, where the e power term, e power minus at, e power minus bt, so is a, b, c are nothing but my poles. So your response depends on exponential term constant, which is my pole of the system, whereas zeros are becomes only coefficients. That means your zero may vary the shape of my plot, but whether it is going to 0 or going to infinity depends on exponential term, plus or minus. Hence, generally we look at the location of the poles rather than the zeros. The other way we know that when you model any system, all the system component information will be lying in the denominator of the system, which is my poles. When you equate denominator to 0, the roots of the denominator are poles of the system. Hence, poles are very important in any system, and location of the pole directly gives the stability nature of the system. So when you look at the next case where I have one pole at origin. When one pole at origin, what is g of t? It is going to be constant. As we know that when impulse response is constant for sufficiently large time, it is called marginally stable system, critically stable system, oscillator response. We give many names to that. Then take the case this, I have one pole at origin, other poles in left of the S-plane. We know that the poles which are lying left of the S-plane will, the impulse responses, they go to 0. The pole at the origin will have the constant, therefore the entire response is also constant. We say it's marginally stable system. But if you have one pole at origin, one pole at right of the S-plane, no, now the system is unstable, because the pole at origin gives the constant, the pole in the right of the S-plane increasing, therefore when you add these two, my response is continuously increasing. So even if you have pole at origin, we have to look at how many poles which are there in the right of the S-plane. Even one pole in the right of the S-plane, even all the poles in the imaginary or left of the S-plane, my system is unstable only. Now we have two poles at origin. So when you write the impulse response, it is t, which means it's continuously increasing. It is also unstable system. We have multiple poles at origin, results in unstable nature of the system. So even if you have the complex poles in the left of the S-plane like this, and you will have your impulse response. When you look at here very clearly, your g of t 2k in t power minus some alpha t into cos of some omega t, which means you have two terms. One is oscillatory term, cos term, other one is exponentially decreasing term. Oscillations are there, but those oscillations are decreasing after sufficiently large time. They are going to 0, so I say system is stable. The poles are real or complex, which are lying in the left of the S-plane, results in a stable system, because it is going to be the impulse response is going to be 0. But same poles if lying right of the S-plane, again we have oscillations, but e power plus t term will appear there, so oscillations are continuously increasing. So poles in the right of the S-plane, whether the real or complex, my system is unstable only. Now, very important case, when you have the poles on imaginary axis, look at there is only one pair of poles. Then when you write the g of t, you will be getting some 2a, some constant into cos omega t, which means we have a continuous oscillations with constant amplitude. So this is called marginally stable system. So one pole at origin is marginally stable, but there are no oscillations. We have constant value, whereas in this case we have oscillations, but those oscillations are constant. Amplitude is constant, frequency also constant. It is called marginally stable system, oscillatory system. Pole at origin is not oscillatory system, but a pair of poles lying in imaginary axis is the oscillatory system. Now two cases, I have pole at origin and also I have one pair of poles in imaginary. It is also gives you constant amplitudes. Okay, maybe that amplitude size may increase or decrease depending upon the pole at origin, but the system gives marginally stable response because we have continuous oscillations. Now if you have more number of pairs, but those pairs are non-repeated. Look at the here, I have one pair here, one pair here. Because of these two pairs I will get this response, because of these two pairs I will get this response, and both the responses are having a constant amplitude. The results, the amplitude may vary, but we have the amplitude is constant, and it is a sustained oscillation, so we call it as a marginally stable. But if those poles are repeated, look at here, the repeated poles here. When you write the g of t expression, we will be getting some constant a1 into t we will be having because of the repeated poles. T extra term will be, again I have cos omega t. Now what does it mean? Because of the term t in the g of t expression, that oscillations are continuously increasing. When oscillations increasing, we know that it is unstable system. So whenever you have repeated poles on imaginary axis, we say it is unstable.